Good afternoon. Today we're going to talk now about some probabilistic modeling used in unsupervised learning, and basically this representation of the relations between the different variables which we use in these graphical models. So I'm going to give a brief overview of some graphical models. Some of them probably, some of you know them from AI, and I'm going to talk also about Markov processes and these hidden Markov models. And these are used to model processes that have usually a time sequence or some notion of sequence, some notion of events that follow one another. So we're going to see some algorithms for using these hidden Markov models and training them. So let's start with the graphical models. This is a convenient representation for relations between random variables, so relations mostly of dependency and independence. And we're going to see some examples, Bayesian networks, which are directed acyclic graphs representing the conditional probabilities and conditional dependency of the different variables. Markov random fields, which are undirected graphs, and they mostly represent the way the diagram works is usually for representing which variables are dependent and how independence can be modeled there. And then we're also going to see the idea of these Bayesian networks that change over time, and then step over to the Markov processes and hidden Markov models. So when we have if we have in this example three different random variables, we can factorize the joint probability distribution as a function of conditional probability. So in this example, we can write the joint probability distribution of A, B, C as the probability of C given a combination of A and B, multiplied by the probability of B given some A, and then the probability of A. And we can represent this factorization in this way, where those that are here in the given part, in conditioning the others, are the parents, and then we put an arrow towards the dependent variable. Of course, we can write the joint probability distribution of these three variables in other ways too. We can rewrite these expressions, and we can use any of these combinations of which one is the dependent and independent variable in this case. So the joint probability distribution can be written in any of these cases here. So we can use this representation to represent some idea about causality or about the actual relation between the variables. For example, this is a classical example. We know that the grass is wet depending on whether it rains or someone turned on the sprinkler system, but we also can model that the sprinkler system will be turned on or not depending on whether it doesn't rain or it rains. So if it rains, we will not turn on the sprinkler and save some water. So this could be a way of factorizing the joint probability distribution of the variables, but representing some notion of causality that we have that we can model in these graphs. So basically, a Bayesian network represented in these graphical models. We have the graph itself, the whole set here. Each node represents one random variable. Each arc represents conditional dependency from one variable to another, and then we can determine on which variable one variable depends by looking at the parents, and also we can indicate observed variables by shading a node. Here it's a bit hard to see because of the cable, but this one is a bit darker. And so we indicate that this variable is no longer unknown, but we actually observe the value. We can also represent parameters as special nodes because these are not random variables, but the parameters of some model we can also represent and include in the graph. To compute the joint probability distribution, we have to multiply all the conditional probabilities of each variable conditioned on its parent. The exception are those variables that have no parents, and those appear alone. So, for example, if we have this Bayes network, we can compute the joint probability distribution of all the variables by using the probability distributions of x1, x2, and x3, and then considering x4 conditioned on its three parents, x1, x2, x3, x5 conditioned on x1 and x3, and then we have x6 and x7 conditioned also on their parents. So x6 on x4 and x7 on x5 and x4. And this graph will represent how the variables are dependent on each other and how we can compute the joint probability distribution for all the variables. So one interesting thing in Bayesian networks is to determine which set of variables are dependent or independent or conditionally independent of another set of variables. So let's see a few examples here. First, the definition and the notation. We say that two variables, A and B, are conditionally independent given C if the joint probability distribution of A and B given C is the same as the probability of A given C multiplied by the probability of B given C. So this means that if we know C, A and B become independent conditions on C. And this can be written in this way, so A and B independent given C. Now, there are different ways of fitting together the variables in these Bayesian networks that will result or not in conditional independence. So, in this case, A and B are not independent from the start because they are both dependent on C. So there is something that makes them related to one another. And we can see this. This is the joint probability distribution for the three variables. So the joint probability distribution of A, B, C is the probability of A given C, B given C, because both of these depend on C, and then C has no parent, appears there alone. If we want to compute only the joint probability distribution of A and B, we have to integrate this for all values, for all possible values of C, but the end result is not just the product of A and B. So A and B are not independent, and this is intuitive because they both depend on C, so they have something in common there and are not independent. But if we know C, so now here there is a slight ghost there. This means that the node is shaded. If we observe C, now we lose the common information that A and B could provide about each other. There is no additional information that A can give us about B or vice versa if we already know C. And we can see this, that the probability, the joint probability of A and B given C is basically the joint probability distribution of all of them divided by C. And if we use the expression here, given the graph, we reach the probability of A given C multiplied by B given C. This means that once we know C, A given C and B given C become independent of each other. So A and B become independent when we know C, and this is basically what we can do to model the naive Bayes classifier. So this would be a representation in graphical models of a naive Bayes classifier. All the feature values are conditionally dependent on the class, but once we know the class, the features themselves become independent from one another if we know which class the example belongs. So this would be a graphical representation of the naive Bayes classifier. When we have this head-to-tail configuration on C, that is, C is receiving an arrow from A and then emitting an arrow to B, A and B are not independent. And this is also intuitive because they have C in common, so there is some information that A and B can share, and they are not completely independent. However, once again, if we know C, if we observe C, the A and B become independent. So A and B are conditionally independent given C. And this, again, we can demonstrate that we can, the joint probability distribution of A and B given C is simply the product of A given C and B given C. And intuitively this makes sense because once we know C, we are blocking information that can come from A to B. There is no longer anything we can know in addition about B by knowing A if we already know C. Now there is one less intuitive combination here, which is when C is at the head of both arrows, so head to head on C. In this case, A and B are independent because there is nothing about A that is determining B or vice versa. So if we compute here, so joint probability distribution of A, B, and C in that graphic model will be the probability of A multiplied by the probability of B, and then C is conditioned on both A and B. And if we marginalize this for C, that is integrate for all possible values of C, we get simply probability of A multiplied by probability of B. So this part is intuitive. A and B are independent because there is nothing making one of them dependent on the other. Only C is dependent on both. But now, what happens if we observe C, if we know the value of C, then conditioned on C, they are no longer independent. So A and B conditioned on C, we can do the same computation we saw previously, but now we don't reach the same value there. So A and B conditioned on C in this case is the joint probability distribution. In this case, it's not merely the product of A given C and B given C. And this is a bit counterintuitive, but we can see with an example. Suppose that C is having access to the internet, A is the cable connected, and B the router working. So C depends on both the cable being connected and the router working. If we don't know anything here, then the router and the cable are completely independent. None of them is dependent on the other. But suppose we know that we don't have internet access. So we know something went wrong when we don't have internet access. In that case, if the cable is connected, it's more likely that the router has a problem or vice versa. So in this case, once we know this one that is at the head of the two arrows, the other two are no longer independent. Okay? So why is this important? We can extend from this. This is I only gave examples of 3 at a time, but we can extend for any size of the graphic model, and we can define these dependent separation rules. So we have 2 sets of nodes, and they are d-separated by C if for every path between the 2 sets that we are considering, there is either a node that belongs to C from which an arrow comes out. So this is one that blocks the information going from one set to the other. And there are nodes that are head-to-head, like this, that do not belong to C or to any descendant of C. That is, all the configurations where knowing about that node will block the information going from one set to the other belong to C, and in the other cases where knowing about that node would remove independence between the other nodes do not belong to C. So in this case, A and B will be independent from one another. Now this is useful because if we can model the relations between different variables in a graph, no matter how complicated the graph, of course I'll only use simple examples, but this can be for any kind of graph that we make. We can identify these independence relations given some observables, and that will allow us to test hypotheses about our models. For example, suppose that we put as an hypothesis that low blood sugar will increase the acidity in the stomach, and this in turn will cause us to feel hungry. So if this is our model about what happens in the body when we feel hungry, then if the model is correct, if we observe the acidity in the stomach and account for that, these 2 variables, blood sugar and hunger, will now become independent. As long as we account for the acidity in the stomach, they do no longer have any relation to one another. On the other hand, suppose that blood sugar is what causes both acidity in the stomach and hunger. In this case, if we account for acidity in the stomach, then it does not change anything. It does not become, the other two do not become independent, because blood sugar is still causing hunger. So in this way, we can test when we observe some variables whether or not our model that describes the causal relations between the different factors is correct. And this can be extended to any, no matter how complex the model is, because we have these independent separation rules. So now, moving on to a different kind of graphical model. In Bayesian networks, we use a directed acyclic graph to represent the conditional dependency. In Markov random fields, we use an undirected graph. So we simply join together variables that are dependent, but we do not indicate which one is conditioned on which variable. So basically, we have a set of random variables. We have this graph, and we consider that non-adjacent variables, non-adjacent nodes in the graph are independent if we fix everything else. So if we block every path between the two of them. And each is independent of all others given the neighbors, if we observe the neighbors. So basically, between two sets of nodes, U and V, these are conditionally dependent on S. If all paths between nodes in U and nodes in V must pass through S. So basically, in these random Markov random fields, we are representing how the variables are related to one another and how we can cut them into independent subsets by blocking the path between them. This is an example from Bishop. For example, here, this group A and this group B become separated, become independent if we observe the nodes in group C, because now there is no path connecting the two groups. In this case, we can compute the joint probability distribution by simply multiplying the probability distributions for the independent group, and we can find them by these cliques. A clique is a set of nodes that are all interconnected, and a maximal clique is a set of nodes that are all interconnected that we cannot increase, we cannot add any node there. So with these properties in the Markov random field, we can compute the joint probability distribution by just considering the cliques and multiplying their probability distribution. For example, here we have, this is a clique here, this is another clique, and so on. There are many combinations here. And this, in this case, this, for example, is a maximal clique, 5, 1, 2, because we cannot extend it by adding another node. 5, 1 would not be a maximal clique because we could extend it by adding 2, and it will still be a clique, but now with more nodes. So these are the maximal cliques that we can find in this graph. So this way we can define the joint probability distribution given a graph of this Markov random field by the product of a function of all the cliques. So we multiply a function of overall the cliques, all the maximal cliques, and we just rescale this by this z factor, because probability must be between 0 and 1, and this can allow us to model the joint probability of the Markov random field. Now, exactly what this function is, we can determine depending on what we're trying to model with this graph. So let's see an example here for denoising an image. We have this initial image with lots of noise, lots of extra pixels here, and we can denoise it and obtain that result by using Markov random fields in this way. We consider a grid of these variables x that represents the map of the image, So this would be something akin to what could be the true image, or some hidden states there that we are not directly observing. And we have these y variables that are the pixels that we are observing. So this would be the x represents the true image, and the y what we observe with the noise. Now each one of these can have two values, -1 or 1, depending on whether the pixel is off or on. And now we can create an energy function, so to speak, that we are trying to minimize to denoise the image. And the idea is that adjacent pixels should have the same value. That is, we are trying to minimize here the product of all the adjacent pixels and summing over all of them. So the product of these two, and then these two, and these two, these are all the maximal clicks we find here. Also, the observed value of the pixel, which is the y there, should match the hidden value of the true image most of the time, because noise should be only a fraction of the pixel. So we do the same for the pairs of all x and the corresponding y. These are the other clicks in this graph. We consider them also with this scaling factor here, and we multiply the two. So basically, these products, if they have opposite signs, this becomes -1, so it penalizes, it increases the energy, because we have a minus sign here. If they have the same sign, then it becomes positive, and it decreases the energy. And now we also have a bias for the pixels. The pixels should be generally on, or we can control that bias. But this gives us the energy function, and now the joint probability distribution. This is based on the Boltzmann distribution, which relates the energy of states of the system to how common they are at a given temperature. We are ignoring here the temperature factor, but we use the same shape of this energy function. And now we want to minimize the energy function and increase the probability of what we find, and that is how we go from here to here, because now the x values here that represent the true image will tend to be on all the on pixels and off on all the off pixels, but will also tend to be similar to those that are in the neighborhood. And when we minimize this function, all these pixels that are isolated here will be turned off, and also the white pixels there inside the letters will tend to have the same color as the letters. So this is one simple example of an application of Markov random field, where we create this probability model for what the true picture should be like, and then we minimize this energy function to denoise it. Now, the big difference between Bayesian networks and Markov random fields, although we are representing dependency between variables, the big difference is that Bayesian networks are directed and specify which variable is conditioned on which variable. They can represent some things that Markov random fields cannot, such as these kinds of relations where one variable is dependent on these other two, but these are the parents and are not conditioned on any other variable. But they cannot represent loops. They must be a cyclical graph. Whereas for Markov random fields, they are undirected graphs, and they can represent these cyclical dependencies here. Now, another thing that we can do is we can imagine that the graph also represents some time variable, something that is changing. For example, we can represent a Markov process like this. A Markov process is a random process in which the result at each time, at each instant, depends only on the previous state. So you can, this is what happens, for example, in Monopoly when we're playing around the board. The probability of reaching each location depends only on where you are at one given moment, and does not depend on what happened in the past. So all these random processes that are blind to what happened in the past are these Markov processes. We can represent this with a Bayesian network by representing at each node the state of the system, and we have this conditional dependency that the state of the system in one node depends only on the state on the node before. So we have this representation of the Markov process, and we can call this a dynamic Bayesian network because we are trying to represent time and the system changing over time. So this can be extended to something a bit more interesting, which is a hidden Markov model. This is actually a very powerful model and very used in many different situations. And the idea here is that we have a hidden state that changes over time, and the state at each instant depends only on the state in the instant before. So this change here is a Markov process. However, these variables, we cannot observe their state. So we do not see the x values. What we see are these y values, they are a bit shaded here, that are the outputs at each state. And the probability distribution of these outputs depends on the state. So depending on what state the system is in, it can output some values with more probability than others. And we can use this to model many different kinds of systems. For example, we could use this to model weather, where there is some hidden state about climatic conditions that we cannot directly observe, but will determine whether it rains or the sun shines or something like that, which is what we observe. Or we can model things like gene sequences, where depending on whether that part of the sequence of DNA belongs codes for a protein or is a promoter region or something like that, it will have different probabilities of having the sequence that we're actually observing. So we can model many things in this way, where we have some hidden state that changes and something that is observable, which is output by that system depending on the state it's in. Another way of representing a hidden Markov model is with a graph showing the different state transitions. Note that these are not now different random variables. This is the x here is the state, but there are three different possible states, and the system will transition from one time to the other between the states with some probabilities. And for each state there are some probabilities of emitting these observables. So this is the epsilon variable, and it can have any of these four values. So what we need to specify a hidden Markov model is these three sets of parameters, basically. First, we need an n by n matrix, where n is the number of possible states that we have. And this matrix tells us the probability of going from state j, of reaching state j at some time t, if we were in state I at time t minus 1. So we have all the probabilities of going from one state to the other. In fact, since these are probabilities, not all of these values are independent, because the probabilities must add up to 1. For many states, there must be a total probability of 1 of reaching all the other states. But basically, we have this n by n matrix that tells us the probabilities of reaching one state as depending on the state we are in. And then we have this k by n matrix, where k is the number of different values that can be emitted in the observable part. And this tells us the probability of emitting some value given the state that we are in. So we need all the combinations, all the states, and all the different observable values. So the hidden states are represented as x. The observable variables here are represented as y. Finally, we need to know the probabilities for the beginning of the sequence. This matrix A here only tells us the probabilities of going from one state to another, but these phi values are the probabilities at the beginning of starting in any given state. So we need n probabilities for all the states. Of course, they are not only n minus 1 of them are independent, because the other is whatever is left for a total of 1, but these are the probabilities for the starting state. If we know this, we can run the simulation by randomly changing state and emitting the observables. So this is a generative model that we can use to generate data of the kind that the model is trying to represent. And this is useful for many applications involving temporal patterns, for example, voice recognition and temporal events, weather, things like that. But although we use this notation referring to time t minus 1, time t plus 1, these models can be used in any situation where there is a notion of a sequence. So time does not need to be actual time, it can be just a position along the sequence. So we can use this for text, for interpreting and tagging text, for sequence comparison and grouping together sequences in bioinformatics and so on. So there are applications that do not involve time, but as long as you can specify a sequence of events or a sequence of states, then you can use hidden Markov models for that. Now, one thing we can do is, suppose we have all the parameters for our model. We know the probabilities of transition, the probabilities of emission, and the starting probabilities, and we want to find, given a set of observables, so we observe what the system is outputting, we want to find the probabilities of the hidden states given that evidence. So this can be done by the forward algorithm, which can compute the probability of the state being at some value at time t jointly with the values that we observe, the observable values up to time t. So basically we're computing the joint probability of what we can observe in different times, in different instances, and the state of the system at the end of that sequence of observation. Now, if we want to do this by combining computing all possible combinations of the states and the outputs, this would be a huge combinatorial problem, and which would not be feasible for reasonable sizes of sequences. But we can do this with the forward algorithm, where basically we can start with this belief state. These are the different probabilities for the state of the system at that time. This belief state for the beginning of, for the first instance, would be the probability of whatever we observed there in the first instance, given each possible state, multiplied by the probability of the system starting at that state. And then we can recursively build from there by using the belief state of the previous instance and the different states there and the transitions for computing what the state can be in the next instance, and so on. And so we can add up the evidence for all the sequence we found after until time t, and obtain the different probabilities for the different states at time t. So this is what we can do if we know the parameters for our model. So we need to know the probabilities of transitions between the states and also the probabilities of emission. Another thing that we can do if we know the parameters of the model is compute the most likely sequence of states up to some point t, given all the observables that we can see during that time. So if we have this sequence of t y values that we observe, we can compute the most likely sequence of states, of hidden states in our system. This is done with the Vitterbi algorithm. I'm not going to detail it here, but just to give the idea, we need to create two matrices with as many rows as the states we have, and as many columns as the number of time instances that we are considering. And now in one of them we will compute recursively the probability of the most likely path to reach that state. This can be done by starting with the initial state. We know those phi values for the probability of the initial state, and also the emission of the observables that we can see. And then we can compute for each state the distribution of probabilities based on what we observed at that instant and what was the state in the instance before. So this gives us the value for the probability of the most likely state at each point, and the other matrix simply keeps track of which was the previous state that led to that one. So in the end, once we compute this matrix, we can trace back along the highest probability by looking at what was the previous state that led to that state at each instant, and so we get a list of all the states and the transitions that were in that path. So this has lots of applications, including, for example, for Wi-Fi, for controlling noisy communications, where basically the hidden states are the actual message that we wanted to receive, while the observables are the actual message plus whatever noise we got in the reception. So this is one way of this is actually implementing on these standards to try to minimize the problems of error of noise in the communication. It's also used for speech recognition, for identifying people by their voice, and in bioinformatics for sequence analysis and so on. So it's not only in those cases where we have a time sequence, but in all cases where we can specify this sequence of states, and then knowing the parameters for the model, we try to figure out what is the most likely sequence of states given what we can observe about the system. Note that there is always these hidden states usually are the most interesting part, which we want to infer from what we can observe. Note that these two algorithms are not the same thing. The forward algorithm that we saw gives us these belief states. These are the probability distribution of the states at each instant, while the Vitterbi algorithm gives us the most likely series of states, so the most likely sequence of states. And the most likely sequence of states does not necessarily have the most likely state at each time instant. Now, this is assuming that we have all the parameters, but we need to train the model first if we want to find the parameters. And here we have a similar problem to ones we saw before. We have a set of observables, for example, the signal that we can receive on Wi-Fi, the image that we see, or the record of the voice of someone that is speaking, for example. But we do not have the hidden state, the actual words the person is speaking, the actual signal that we should be receiving from the network, or something like that. So, if we knew everything, if we knew the y's and the x's, we could compute from a large enough sample the probabilities of transitions, the probabilities of emission given each state, and so forth. So we could compute the parameters if we knew everything about the system. However, we don't know the states, the hidden states of the system along the process, and we would need that to compute the parameters. On the other hand, if we know the parameters, we can estimate the hidden states of the system. This is what we saw, for example, with the forward algorithm here, where we can estimate the probability distribution of the state at each time if we know the parameters and the epsilons that we can observe. So this is basically the same problem we saw several times now of using expectation maximization. We will need an initial guess on the parameters, then try to estimate what is the expected distribution of the hidden variables, and then use that to maximize the likelihood of the parameters and repeat. So in this case, we will do two things here. We have these alphas and betas, but the general idea is the alphas are the belief states similar to what we saw in the forward algorithm, where we're going to compute the probability distribution of the state at each time t, given all the things we can observe so far, up to time t. So all the epsilon values in the sequence until that instant. And these gives us the probability distribution of the state of the system, given all the evidence up to that moment. And then we have this backward path with which we compute the probability of emitting that the final part of the sequence, so going from t plus 1 up to the end, given that the system is at that state at time t. So if the system is at that particular state in this time, what is the probability of the next part of the sequence from t minus 1 to t plus 1 to the end? So in this case, in the forward algorithm, we start with the initial probability of the state and the probability of emitting the symbol that we have observed, and then we build from that by considering the transition probabilities between the state and the emission at each time until time t. And for the backward path, we start at the end with a value of 1, because at the end there is no more sequence to output. But then we go back by considering the emission probability of the sequence at the end, the transition, and the going backwards from that final probability until we reach time t plus 1. So basically, we are looking at two things here. Given the evidence so far, so all the sequence up to time t, what is the probability of each state at this instance? And then, given each state at this instance, what is the probability of emitting the sequence up to the end? And now, using this, we can compute the probability of being at some state at each instant, given all the sequence that we observed, so all the y values, both before and after this instance. So this is basically considering the evidence before and the probability of the emission afterwards, and marginalizing this over all the combinations. And we can also compute the joint probability of having one particular state at one instance and another state at the next instant. So we compute the joint probability of the pairs of states that appear along the process. And this, again, we can use the evidence that came before and after, and the emission probabilities there, and the probabilities that we assumed we knew about the state transition. Note that this A is the matrix that gives us the probability of going from one state to the other, and this B is the matrix for the emission of observables from each state. And we marginalize that, so we divide by the total of these probabilities. So what we get here is basically the probability of being in one state, given all the evidence we can observe, and the joint probabilities of pairs of consecutive states, given all the evidence that we observed. So we got these assuming we knew the right parameters, but now we can use these for the maximization step. Now that we have an estimate, not only we know the observables, but we have an estimate of the probability distribution of the hidden state, we can use that as a likelihood function, and so maximize our likelihood by adjusting the parameters. And this turns out to be the new pi values will simply be the probabilities of the state at the initial time. Then the transition state, we go look at the joint probabilities of consecutive states, and we use that to recompute the matrix that gives us the probability of going from one state to the other. And we do the same for the emissions, finding all those examples where each epsilon value is emitted, and then using the probability of that state and marginalizing by the overall probabilities of the state. So basically, this is the expectation maximization algorithm. We start in this first part. We are estimating the probability distributions of those hidden states that we cannot see. So we compute the joint probability of hidden states and the emission and the future emission given each individual state. And then we can compute the joint probability of the pairs of states from which we can get the transition probability. And once we have this in the expectation part, we maximize the likelihood by adjusting the parameters. We get a new set of values for the parameters, and then we go back and repeat everything until it converges. Now, this does not guarantee a global optimum. It can get stuck on a local optimum, and there's always the problem of overfitting. So remember that we are considering the probabilities of emitting different values along the process and all those transitions. So our sequence must be long enough that we cover all the possibilities. We have the number of states in the matrix for transition is squared because we have n by n possible transitions, and then for each possible state of the hidden variables, we can emit any of the symbols. So we have k by n parameters there. If the sequences are not long enough, then our system will probably overfit to the only examples it finds there. But we can use this with unsupervised learning. If we have a set of examples, for example, we have a large database of gene sequences, we can feed it into the hidden Markov model and create a statistical model of what the sequences of symbols in that DNA sequence, for example, is likely to be. So this can be used to also to classify, not only to cluster, but to classify any sequential data. For example, to classify, we can start with sets that are previously labeled, and we can train hidden Markov models with these sets, and then for any new example, we will see which of the hidden Markov models has the highest probability of outputting that particular sequence. This can be done this is what is done in the PFAM database, the protein families database, to aggregate proteins by the amino acid sequence. It's used for speech recognition, for an analysis of phenomena that change over time, and so forth. We can also use hidden Markov models to generate new examples of the same kind of sequence that we found. So we can use this for speech synthesis and creating new sequences, text generation, things like that, because once we have the parameters there, we can run the simulation, change the states, the hidden states with some probability, and emit observables from those states with the probabilities that we compute. So to sum up this part of the graphical models, we saw how to represent dependency and independency between different variables in a graphical way. This makes it easier to find, for example, what variables we need to observe to test some hypothesis or to represent causal relations between the variables. And we saw this hidden Markov model where we model a Markov process, a process of random change that has no memory before the last iteration, but we model that in a set of hidden variables. And then there are some observables that are emitted, and although this seems like a strange abstract model, it can fit a lot of real case problems where we have something that we are observed that, for example, changes over time, but we need to infer what is behind that emission. For example, we have a fragment of a sound wave, and we need to know which word is being spoken at that time. Or we have a set of DNA, a part of a DNA sequence, and we need to know what that is doing in the organism. If it's part of a protein, if it's rubbish, if it's a promoter sequence or something like that. So this way we can model many of these problems where we want to infer something that is hidden from those things that we can observe. And we saw the forward algorithm to get the probabilities of the hidden states once we have the parameters for the model and we observe a sequence of those observable values. The Vitterbi algorithm to find the most likely sequence of states, and also the Baum-Welch algorithm, which is a way of implementing expectation maximization here to compute the parameters of the model. So we have in this section of Bishop's book lots of details about graphical models and hidden Markov models here.